Welcome to Team Ninja's Fluid Mechanical Dissection project. In this video, we will be analyzing the fluid mechanics of a wet-dry vacuum, most commonly known as a shop vac. Shop vacs are useful because of their strong suction and ability to vacuum up a large variety of materials, such as glass, metal shavings, water, dust. The specific shop vac that we used was the shop vac 6-gallon with 3.0 peak horsepower. Inside of this vacuum is a radial pump with a radial fan. During this video, we will explain how the fluid mechanics of the shop vac enable it to perform in the way that we want it to, by first considering the streamlines within the vacuum.
Given that we are able to describe the flow through our shop vac as being steady, incompressible, as well as having a low Reynolds number, we are able to apply Bernoulli's equation with losses as we follow the flow along the streamline. As shown here, we can trace the flow's path along a pressure gradient where the fluid moves from high to low pressure areas up until the radial fan, where there is a pressure discontinuity across the fan. Following the radial fan, the flow moves from high to low pressures as well. More specifically, we can trace the path of fluid flow starting at the suction hose inlet, which sucks air in from the atmosphere, increasing the flow's velocity and thus decreasing the flow's static pressure. This pressure drop is what provides the force that allows the shop vac to suck up the water or debris. From the hose, we can trace the flow's path to the inlet of the collection bucket, which has an even lower pressure than in the suction hose. The inlet of the collection bucket has a hooked vane, which causes the flow to have a rotating circular path. This circular path allows time for the water or suction debris to fall to the bottom of the bucket and allows for all parts of the air filter to be utilized. Once the fluid has passed through the filter, the fluid accelerates towards the radial fan, where the fluid enters the fan through the center, follows along the vanes, and is radially accelerated up and out of the fan chamber into the outlet channel. Bernoulli's equation with losses cannot be applied to the flow across the radial fan due to the aforementioned pressure discontinuity. Inside the outlet channel, the flow experiences a higher pressure that is greater than the atmospheric pressure. This pressure gradient encourages flow to move through the outlet channel to the exhaust outlet and out into the atmosphere at atmospheric pressure.
In order to characterize the pump, we can calculate non-dimensionalized parameters to show how they depend on the pump diameter and pump speed. Although our vacuum was no longer operable, the vacuum in the forklift studio functioned similarly with the radial pump, so we decided to take measurements from it for our calculations. We were able to measure the delta P, pump diameter, hose diameter, and power using a pressure gauge, tape measures, and ammeter, and found specifications online for the max flow rate and angular velocity of the pump. It's important to note that the values that we found are the pump not operating at max efficiency. This can be seen in our pump efficiency calculation, in which we got about 18% efficiency for a pump. The following non-dimensionalized parameters explain to us whether or not a pump is performing well given a set of conditions. We also calculated the specific speed and specific diameter of our pump. The specific speed of the pump tells us to compare it to other pumps whether it has to run fast or slow to achieve a task. Similarly, the specific diameter tells us compared to other pumps whether the pump needs to be bigger or smaller to achieve a task. Here we show the specific speed versus specific diameter chart for various pumps. Although we expect centrifugal pumps to have a high pressure and low flow rate, our specific speed and specific diameter calculations end up closer to the axial flow pump range. This can be explained by the fact that our pump is not necessarily running at maximum efficiency, at which point this graph cannot be applied to characterize the pump. Given our efficiency of about 18%, it can be seen that our pump has the necessary pressure difference for suction of both water and dry particles, which is unique to a shop vacuum as opposed to other vacuums that cannot necessarily intake water or wet materials.
Let us consider a section of the shop vac tubing. As the fluid is moving through the tube, it experiences viscous effects near the walls. The fluid sticks to the walls. This no-slip condition means zero velocity of the wall and causes the tube to be pushed forward while the fluid is pulled back, contributing to shear stress. If we consider the velocity profile in the tube, we would initially observe a region of slow-moving fluid near the surface. In between these boundary layers, the viscous effects are negligible, so our velocity would remain more or less constant. However, as the fluid continues to move, the boundary region continues to grow until it covers the entire tube, and we've moved into the fully developed flow region. In this case, velocity is only a function of the radial direction. Now we would observe a parabolic profile with the maximum velocity at the center line. The velocity profile is important because it can tell us about the drag force, which is used for calculating the Bernoulli equations with losses.
Finally, we will calculate the Reynolds number. The same constants and values from the textbook and shop vac specifications are used. For the Reynolds number, we must first find the speed of the fluid and then plug that into the equation. As seen here, an anemometer was used during the lab to find the speed, due to the losses that needed to be accounted for, and the inlet speed was found to be 3.3 meters per second. Plugging this into the Reynolds number equation, using the hose diameter, we get a Reynolds number of 6,985. Because the Reynolds number is much greater than 500, this fluid has turbulent flow. Thank you for watching.